live. Okay, we'll see how this works. Okay, so basically when we're doing region between curves, when you did integration, you did you did area under curves. So basically between a curve and the x-axis. Now we're going to do between curves. And the best way to show you is to draw you a pretty picture. This is just a pretty picture for fun. And I'm going to draw an x and y axis. I froze it. It's coming. Hang on. Let it go. There it is. All right. So I'm going to have an upper curve, and we'll do that in blue. And we're going to call this one f of x. And then I'm going to have a lower curve, and we'll draw it like this. Here's my lower curve. That's g of x. And if I want the region between the curves, I want this area right here. So I'm going to do a different color. I want this area right here. Well, the easiest way to do this, I'll shift this up a little bit for you, is I'm going to resketch it, sort of. So I'm going to have the upper curve, it's about there, close enough. You get the idea, right? And if I'm going from, this is going to be my A to suppose this is going to be my B. If I'm integrating from there to there, is that the area under f of x? And to get that region, don't I just need to subtract off the area for g of x? Right? And this area between A and B is just this. Right? If I take this and I subtract that, do I get that? Do y'all see it? Oh, I was going to erase something. I don't know what I was going to erase. So anyway, let me draw it in here. So I'm going to draw it in here. So basically what's going on is you had the blue and you're going to subtract off the red. You subtract that off. Do you get what's in between? Okay, so let's think about that. Does that mean that if I'm doing the area under f of x, it's just the integral from a to b of f of x dx? And if I'm doing this one, this is going to be, so this is the integral from a to b of g of x dx. This is the integral from a to b of f of x dx. And if I subtract the two, will that give me the area between? That's what this is all about. But we don't want to do that, do we? We don't want to do it as two separate problems. If I'm integrating f of x from a to b and I'm integrating g of x from a to b and I'm subtracting them, can't I just subtract f of x, can't I just write f of x minus g of x and just integrate the whole thing at once? And that is what we're going to do. So that's physically what's going on, but a better way to think about this is to think in terms of, so I have this length right here. Do we agree that that length right there is every single time going to be f of x minus g of x if I want a positive length? Every single time, isn't that true? Yeah? And if we integrate that, will we get that region between? That's the shortcut. But this is what we're doing when we do that. We take the region under f of x, we subtract the region under g of x, and that's what we're doing. Okay. So I'm going to give you an example, and then I'll show you some tricks. So this is our first example. We may not make it very far. These take a little while, because I can do them really fast, but y'all can't graph. And guess what? You need to be able to graph. It really helps. So we are going to find the area between f of x equal to x squared minus 4x plus 3 and g of x equal to negative x squared plus 2x plus 3. And you really need to be able to graph quadratics because they really like it. So first off, I don't know if you noticed, but in that other graph I did, I had a point of intersection. So it's always nice to know if there are points of intersection. In this case, since I've got two parabolas, does f of x open up and g of x open down? Do y'all see that, right? So if I'm really lucky, they'll intersect at some nice points. And then that makes it really easy. I just integrate between the points of intersection. Sometimes that's not true. Sometimes there's the third boundary defined. We'll get to those kind. But the first couple of kinds of problems we'll do, we're just going to find points of intersection. So points of intersection, we have to find those first. Points of intersection, I abbreviated. Points of intersection, right? So I'm going to set x squared minus 4x plus 3 equal to negative x squared plus 2x plus 3. I'm going to get everything to the same side, and I'm going to get a 2x squared. And then I have 4x, and I've got a negative 4x and a minus 2x, so it's minus 6x. And then 3 minus 3, that goes away. That's convenient, isn't it? That equals 0. Well, if I factor out a 2x, I get x minus 3. And my points of intersection are x equal to 0 and x equal to 3. Does everyone agree? Yeah. Nothing this easy would be in the calculator section of the AP test, but on the calculator AP test, will they give you some on the calculator section where you have to find those points of intersection using the calculator? They will. They will do that to you. All right. So let's graph these so I can show you how this works. And it is best to graph these now. To make it really easy, we're just going to pick nice whole numbers to graph. So for f of x, oh, actually, let me change colors. I'll make f of x blue. So f of x is equal to x squared minus 4x plus 3. I could factor it, but I'm not going to bother. I have x and y. I'm going to pick, I know that they intersect at 0 and 3, so I'm going to look between 0 and 3 and hope I get lucky. I know what this looks like, so I know it's going to work. So I go 0, 1, 2, 3. I put in 0, I get 3. I put in 1, I get 1 minus 4 plus 3, I get 0. I put in 2. That gives me 4 minus 8, that's a negative 4, plus 3, that makes it a negative 1. Put in 3, I already know that's going to be 0. Right? Everybody still with me? Okay, then my other function, g of x, is equal to negative x squared plus 2x plus 3. I have x and y for them. I'm going to pick the same x values. 1, 2, 3. At 0, it's 3. That's convenient since that's a point of intersection. You notice that was our point of intersection right there? They should match. If they don't, go back and fix your silly mistake. Put in 1. I got negative 1 plus 2 plus 3. That means I'm going to have 4. Put in 2. I got negative 4 plus 4. That's going to go to 0. And I've got 3. Plug in 3. It's 0. Notice my points of intersection have the same coordinate. I know I did it right. Now we're going to graph it. And this is where it comes in handy to have grid paper. Area between curves, it's kind of nice. When we get to volume of curves, it's going to be absolutely necessary. Y'all will have really trouble seeing all this if you don't graph it on a grid. Because I can graph without a grid, but y'all have not had enough practice. All right, so here is my curve. So I'm going to make this, that's 1, 2, 3. I got 1, I got a negative 1, and then I got to go 1, 2, 3. I should have made it bigger. Do I need to make it bigger? We'll see what it looks like. Okay, so for f of x, my points are at 0, it's 3. At 1, it's 0. At 2, it's -1, and at 3, it's 0. So it's a nice parabola like so, all right? And then my other one, g of x, starts at the same place, but it goes up to 4. And then it comes down to 3 at 2. And then it intersects here. So it goes like so. This is g of x. This is f of x. And I want to find the region between. So I'm just going to draw really, that's my representative cross-section. You remember how we did an infinite number of rectangles to find the area under of a curve when we did Riemann sum? Do y'all remember anything from last year? Well, these are still rectangles. We're putting an infinite number of them in there, but instead of being just the f of x, this rectangle is equal to f of x, of g of x, g of x minus f of x. So we're filling it in just like we did when we were doing the Riemann sums, but now instead of just being f of x, where it was the f of x going down to the x-axis, it's going between the curves. Got it? If I am talking about something where everything, there's one curve that's always upper and one's always lower, then we're always going to do upper minus lower. And if you always do upper minus lower, will it always give you a positive length? That's kind of handy if you're trying to find area, because you want it positive. Okay, that means that to find the area in between those curves, I got to go from A, every single time my area between is going to be the integral from A to B of that L of x dx. In our case, we're going from 0 to 3. Those are my points of intersection, and my upper curve is the g of x, and my lower curve is the f of x. So let's find what that is so we can make our lives a little easier. So my L in this case is going to be g of x, which is the negative x squared plus 2x plus 3, and all that's minus the x squared minus 4x plus 3. And so what does my length equal? Negative 2x squared plus 6x, because the 3's cancel out, right? So that's what I'm going to integrate. So my area is equal to the integral. My points of intersection are 0 and 3, and I'm going to integrate negative 2x squared plus 6x dx. Did that suddenly get really easy? Didn't seem like it was going to be that easy, but it is. It's amazing how it all falls out ever so nicely. So what is the antiderivative of negative 2x squared? Right? Negative 2/3 x cubed. What is the antiderivative of 6x? 3x squared, because I'm going to have 6x over 2, which is 3. All of that is evaluated from 0 to 3. So this equals negative 2/3 times 3 cubed, and then it's plus 3 cubed, right? All of it minus 0. Okay, to make my life easier, I'm going to look at this and go, oh, instead of 3 cubed over 3, I'm going to say that's 3 squared, which is 9. 9 times 2 is 18. So this becomes a negative 18. Hang on, let me change that. Equals a negative 18 plus 27, which means it's 9. The area between the curves is 9 units squared. We're not worried about the units. What do you think? Not too bad? Yeah? Okay, that is a basic problem. So rather than me blathering on, what I would like to do instead is, how about, I'll try them, and then I'll show you something more complicated tomorrow. Hang on. I gotta see how many days I've got for this. Hang on, I gotta look. That's tomorrow. Let me look on the calendar. Hang on, pause this. Okay, so that's a really straightforward one. Maybe. No, I want that one. Okay. Really straightforward, right? But what happens if it's not always the same? What if the curves, what if it's like a trig function or a cubic where it switches which is upper and lower? Uh-oh. Let's figure out how to do that. Okay, so this is our example 2. For example 2, we're going to find the area between f of x equal to 3 times x cubed minus x, and I'm going to be nice and we're going to say g of x is equal to 0. But don't get all excited because that's not that great. That's the x-axis, right? So we got to find points of intersection. We're going to set 3x cubed minus x. Oh, sorry. There we go. I'll get there. Equal to 0. Can I factor something out? Yeah, I can go 3x times x squared minus, oh my goodness, can I keep factoring? I can you? 3x times x minus 1 times x plus 1 equals 0. So what are my points of intersection? X equal to -1, x equal to 0, and x equal to 1. When you get more than 2 points of intersection, that's when you should be suspicious that you might have something weird going on. So we need to graph this puppy. So over here I got x, I got f of x, because I don't have to worry about g of x, it's 0, right? So I know I'm going, but I got to have -1 in there, so I'm going to have -1. I'm going to have, I got a better idea. Hang on a second. I had a brilliant idea before. Let me erase this. We're just going to sketch this puppy. And we're going to do our curve sketching to help us. Just that idea of a table. But instead of having hard values, I just need to know up and down. I just need to know if f of x is above or below the x-axis, right? This is a sketch. We don't need perfect sketches. We just need to know up or down. So I know that the points of intersection are -1, 0, and 1. At those, my f of x is 0, and it intersects g of x. No, because all I care about is the points of intersection. I want to find between those two. Just trust me on this, okay? Just go along, and after you get the hang of this, you'll realize what we're doing. All right, so I'm going to put a -1/2 in here, and I'm going to put a 1/2 in here. And we're going to look in the factored form. If I put a -1/2 in here, that's negative. This is negative, and that is positive. So I am positive this is positive, and it is above the x-axis. If I put a 1/2 in, the first term is positive, the second one is negative, and the third is positive. So I am sure that it is negative. So I know it's below the x-axis. And now we're going to sketch it. And you'll see what I was talking about. So I slide this up. I'm going to draw something nice and big for you. Oh, look at how good I'm doing on drawing a straight line. Isn't that amazing, ladies and gentlemen? I didn't need that much straight line. I'm going to do this again. I don't need quite that much. And going down here. Nice and straight. Isn't that amazing? Okay, I'm gonna make this nice and big for you. That's 2, 4, 6. That's 1, 2, 4. Oh, go away. 2, 4, 6. That's 1. And then I don't know how much I need to go up. I just know I need to get up. Okay, now we're gonna sketch it. We know it is 0 at -1, 0, and 1. That's -1 and that's 1. I know that it's above here. I know it's below there. So it's a cubic. Is it going to go like this? Something like that? Right? Actually, it's going to be symmetrical here, but don't worry about it. It doesn't even matter, does it? Since my g of x is this line right here, this is g of x. This is f of x. Does it switch which one is upper and which is lower depending on where I'm at? So over here, this is my first L. This L is equal to f of x minus g of x. This L is the second L. It's equal to g of x minus f of x. Do y'all see why I had to switch it? This is going to happen with cubics, and it's going to happen with trig functions. Yes, eventually I am going to do the integral, and you're going to find all the places where sine and cosine meet, and you're going to have to find the regions between, and it's going to switch on you, isn't it? Yes, it is. Okay, so if I want to find, so what I'm doing is, I'm finding this area right here, and this area right here, right? And when they say area between curves, they don't want you to take into account that this is positive and this is negative. They really do just want to know a positive area between the curves. Do you understand what I just said? It's different than just, this is not the velocity and we're accumulating position. In this case, they really do want to know between the curves, you're keeping it all positive. So how am I going to do this? I am going to integrate, so my area between the curves is integral from -1 to 0, and I'm going to use the length 1, which is f of x minus g of x, which is just the f of x, right? So it's going to be, I'm going to go ahead and distribute. It's 3x, was it cubed? Yes. Minus 3x dx. Did I just distribute for my f of x? And then I'm going to add the region when I integrate from 0 to 1, but in this case, is it 0 minus that? So is it all negative? So is it going to become 3x minus 3x cubed? Do I just switch the signs, right? Because this is 0 minus 3x cubed minus 3x. And is that how I got that? So once I do that, is that easy? The hardest part was getting it all set up and making sure I had it all straight. And that's why I want you to graph. And now we need you to get fast at it. We don't need artistically perfect graphs. You need sketches that are sufficient for you to tell upper minus lower. Got it? Okay, here we go. What's the antiderivative of 3x cubed? 3x what? Over. And what's the integral of 3x? Evaluate from -1 to 0. Plus, this one is going to be, and I'm going to put brackets just so you don't get them mixed up. It's going to be the 3x squared over 2 minus the 3x to the 4th over 4, and this one's evaluated from 0 to 1. So when we do this, first it's 0 minus, put in a -1. Since it's to the 4th power, we don't care, it's just 3/4, right? And then we put a -1, we squared, we don't care, it's minus 3/2. So when I distribute the negative sign for this part right here, it becomes the 3/2 minus 3/4. Well, 3/2, double it, that's 6/4. What's 6/4 minus 3/4? 3/4. Okay, for this one, plus, for this, it's going to be 3/2 minus 3/4, and then it's minus the 0. So it's going to be plus another 3/4, which means it's 3/2. That's fair game for a non-calculator question. That's about the level of difficulty on the AP test. I will admit, some of the ones on the worksheet, you know where your worksheet is, by the way? Did you look on the back of yesterday's sheet? That's where the area worksheet is. That's what you're supposed to work on today. Some of those are a little more difficult than that. Now, before we finish, I need you to know my very most favorite functions for this purpose. Most favoritist. Mrs. White's favorite functions for this. Does that mean you need to be able to graph these really fast and you need to practice them? AV means area volume. My very most favorite are x squared and x squared of x. So I'm literally just sketching it. We're going to call that the square root of x. We're going to call that x squared. Really. That's how fast you have to be able to sketch these. So in this case, this is f of x equal to x squared. In the other case, that was g of x. Is g of x greater than f of x everywhere between 0 and this is 1? And that is 1, right? So if we're doing this one, and these are all of our rectangles we are filling it with, is one of these lengths, if we define this as this length, every single time if I want it to be positive, is it the square root of x minus x squared every single time, right? And we all agree that the points of intersection between x squared and square root of x are 0 and 1. Yeah, so I don't have to show you that, do I? No. So if I want to do this area, is it really easy? Oops, let me get rid of that color. Let me get black. So show it up better. Y'all ready? Are y'all ready for the area? So area equals the integral from 0 to 1 of x to the 1/2 power minus x squared dx. What's the antiderivative of x to the 1/2? X to the 3/2, and it's 2/3, right? Because I do the reciprocal because I'm divided by 3/2. What's the antiderivative of x squared? Anybody awake? X cubed over 3. I'm evaluating from 0 to 1. It doesn't get any easy. Do you see why I really like this one? Y'all hate the fractional powers, but I love it because it's easy to evaluate. So what do you get? You get 2/3 minus 1/3 minus 0 is 1/3 every flippin' time. It's that easy. And I will remember my easy button tomorrow. You have a quick quiz tomorrow, and we will finish up area between curves, and we'll start volume the next day. So your quick quiz tomorrow is over the 6-1, but it's not going to be a velocity one, I'll tell you that right now. It's not going to be a particle motion, so it's going to be one of those other kind. It's going to be a wordy problem. You have to read it, figure out what your starting place is, what time your starting is, and figure out what the rate is and use it. Fair enough? Okay, I am stopping the recording now.